lambda c. So we make use of these relations comfortably while solving these problems in this unit. Okay. So these are some of the relations between lambda g, lambda naught and lambda c. So now let us define what is the wave impedance and how we represent this wave impedance. So this is the wave impedance. So generally we represent this wave impedance as Zg, guided wave impedance, as Zg, as because it is propagating through the rectangular waveguide. So Zg represents the wave impedance of the wave that is propagating through the rectangular waveguide. So it is defined as the ratio of the strength of the electric field in any one transverse direction to the magnetic field in another transverse direction. For example, how we are going to represent this Zg is Zg is equal to, if you take electric field in x axis, because we are taking the Cartesian coordinate system. So this is x, y and z. So if you take the electric field along this x axis, then any other transverse direction, that means you can take it on y or z, then generally z is considered for the propagation of the wave. So we consider the electric field on x axis and the magnetic field on the y axis, or we can consider the electric field on the y axis and the magnetic field on the x axis. Either we can take the ratio of the electric field on x axis and magnetic field on y axis, or electric field on y axis and the magnetic field on x axis. So generally it is defined it as Ex by Hy, okay, or we can also define it as minus Ey by Hx. Okay. So the wave impedance is defined it as Ex by Hy or minus Ey by Hx. Right, we have already defined these field components. So these field components are defined depending on the TE or TM modes that are propagating. Anyhow, let us see what is Ey and Hx here, how we have defined the field expressions. So Ey generally is expressed as minus gamma by h square dou Ez by dou y plus j omega mu by h square dou hz by dou x. So this is the field Ey in terms of Ez and Hz. Similarly, we can get Hx. Hx we can represent it as minus gamma by h square dou hz by dou x plus j omega epsilon by h square dou Ez by dou y. Can use Ex by Ey or minus Ey by Hx, we can generally use. So these are the relations we have, and depending on the TE mode or TM mode, we have, if it is TE, for TE transverse electric mode, Ez field component is 0, and for TM mode, Hz field component is equal to 0. Okay. For example, if we consider the wave for TE mode, then Ez is equal to 0. That means this field component becomes 0. Ez is equal to 0. That means this term here will become 0 and here this term will become 0. Okay. So, we can substitute this Ey by Hx here, so that we can get for the TE. So, let us see what is the wave impedance for the TE mode and what is the wave impedance for TM mode. Okay. So, first if we say the wave impedance in the TM mode, that means, so for the TM mode we have Hz is equal to 0, that means these terms are going to be 0, and so we are going to divide these terms. Okay. So, we are going to get the Zg in Tm is equal to minus gamma by h square dou Ez by dou y. Actually this is Ey, and here we have another minus Ey by Hx. So, in the Hx we have j omega epsilon by h square dou Ez by dou y. Okay. So, we substitute that j omega epsilon by h square dou Ez by dou y. So, this will get cancelled, h square will get cancelled, and here we have the 2 minus. So, the wave impedance in Tm mode we can write it as equal to gamma by j omega epsilon. So, what is this gamma? Gamma is the propagation constant, and while the wave is propagating through the waveguide, then there is no attenuation. So, we can write this gamma is nothing but equal to j beta for the propagating wave. So, this j gets cancelled, and so this is equal to beta by omega epsilon. So, let us substitute beta. We know that beta, so we write Zg in Tm mode is equal to beta, that is root mu epsilon omega square minus omega c square by omega epsilon. Okay. And here it is root epsilon is there and here epsilon is there. So, this term we can write it as root mu by epsilon and if you take omega as common from this, the omega gets cancelled, and so we are going to get into root 1 minus omega c by omega whole square. So, this root mu by epsilon can be considered it as the eta, and this can be written it as root 1 minus omega c by omega whole square. We can write it as fc by f whole square, or we can write it as lambda naught by lambda c whole square. And what is this eta? Eta is the intrinsic impedance. Eta is nothing but equal to root mu by epsilon, and this we call it as intrinsic impedance. Okay. And for free space, this intrinsic impedance free space or for air, we can consider it as equal to 120 pi for air medium, or we call it as free space. Okay. So, the guided wave impedance in Tm mode is equal to eta root 1 minus lambda naught by lambda c whole square. In a similar way, we can also obtain Z waveguide impedance in TE mode. Let us go for the derivation. Okay. So, now wave impedance in TE mode. So, this is represent as ZG TE. So, how we define this wave impedance? So, this also we take it as minus Ey by Hx, but as it is TE mode, okay. So, in TE mode, Ez is equal to 0. So, this Ey and Hx are expressed in terms of Hz. So, the Ey in TE becomes Ey is equal to minus plus j omega mu by h square dou hz by dou x, and hx becomes minus gamma by h square dou hz by dou x. The Ez term has become 0 in these expressions. So, now if you divide these two terms, okay, you are going to get this term is going to get cancelled, h square is going to get cancelled. So, let us substitute that here, and here we have the minus. So, this minus and this minus gets cancelled, and we are going to get j omega mu by gamma. But we know that gamma is equal to j beta, because for the propagation alpha should be equal to 0 and the gamma is equal to j beta. So, therefore, ZGTE we can write it as equal to omega mu by beta, and as we already know that beta is equal to root mu epsilon omega square minus omega c square. Let us substitute the same here, and so we are going to get mu and root mu here. So, again it is root mu by epsilon 1 by root 1 minus omega c by omega whole square. So, or if we consider this root mu by epsilon as the intrinsic impedance eta, we can write this ZGTE is equal to eta by root 1 minus omega c by omega, we can write it as fc by f whole square, or we can reverse this and can write that it is equal to eta by root 1 minus lambda naught by lambda c whole square. So, this is the wave impedance in TE mode. ZGTE is equal to eta by root 1 minus lambda naught by lambda c whole square. Again here eta is a intrinsic impedance or a free space impedance. So, eta is equal to 120 pi for air or free space medium. Okay. So, this is the wave impedance in TE mode. So, for TM it is eta root 1 minus lambda naught by lambda c whole square, and for TE it is eta by root 1 minus lambda naught by lambda c whole square. So, we have derived the expressions for wave impedance in TE mode and TM mode, and let us go to the summary of this session. So, in the beginning we have derived the expression for the guided wavelength, phase velocity and group velocity, and has obtained the relation between phase velocity and group velocity as Vp into Vz is equal to c square, and also we have derived the expressions for the wave impedance in both TE mode and TM mode. Okay.